In Domingos' book, The Master Algorithm, he discusses 5 tribes of AI and their typical approaches to solving problems. Each of these tribes uses some method of evaluation to gauge how well their algorithms are performing. While there are more scoring methods to evaluate a function, we're going to focus on the ones presented in Chapter 9, which illustrate a hypothetical city which he believes surrounds this conceptual pillar known as the master algorithm. From the 5 tribes, he has borrowed accuracy from the symbolists, squared error from the connectionists, fitness from the evolutionaries, posterior probability from the Bayesians, and margin from the analogizers. With all of these evaluation methods, there are some strategies used to minimize the risk of overfitting a model. One of the most tried methods is to test a model on a set of data which it has not yet seen. This works well to check for overfitting, but preventing overfitting in general can also be done by creating a preference for shorter rules. This ideology is also known as Occam's razor. One method for reducing overfitting is considering statistical significance. This is a concept where if a change does not provide significant increases to our model's accuracy, then we'll ignore it. Reducing overfitting with these methods will typically reduce the overall performance on the training and test dataset. However, it should create a better generalization, which is our goal. The shorter rules provided will also reduce the time it takes for this model to train and use, which may also be something to consider. When evaluating a model, it also helps to understand not only when our models are wrong, but how they are wrong. We find that models may have a bias, a variance, or both. Domingos' book uses the example of playing darts to describe these concepts. If a model is consistently missing the mark but is off by about the same amount each time, we say it has bias. If it is consistently missing the mark but it is unpredictable, then it has variance. A model can have both bias and variance, shown in our example on the top right, where our shooter is missing the bullseye high and wide every time, favoring that quadrant of the dartboard, but still wildly inconsistent. From the symbolist tribe, we have the accuracy evaluator. This is the most straightforward evaluator we have for our dataset. What is the number of correctly predicted examples out of total examples? This method is not always the best option, but it works particularly well for models which can be broken up into a series of yes or no options, or classification problems. If we wanted to create a model to correctly guess the exact price of a house, and we use accuracy as our metric, we would probably have a very low score, even if the model isn't too far off. From connectionists, we have squared error. The mean squared error, if the name doesn't give it away, is the average distance between predicted data points and the actual data points, just squared. This, opposed to accuracy, is much better at gauging how far off a model is in its predictions, and can allow us to adjust accordingly, and minimize that error. One important feature used here is that this method requires the use of a continuous function, which is typically, but not always, the sigmoid function. The sigmoid, or as Domingos refers to it, the most important curve in the world, looks much like an elongated S-curve. This allows for a smooth transition from 0 to 1, rather than an explicit on or off binary state. What makes the sigmoid so special is the fact that every function can be approximated by a sum of this function. From the evolutionaries, we have fitness. Evolutionaries use a concept known as genetic programming, which intends to evolve programs the same way that nature evolves organisms, by taking the best traits of each program and passing them on. This looks much like survival of the fittest, no pun intended, where only the strongest traits survive. Fitness refers to how well a function is being approximated, and thus is simply just another name for a scoring function. With a concept like that, the evaluator from the evolutionaries is simple. It is whatever is best suited towards the job at hand. This could even mean that the evaluators are accuracy or squared error, should they perform better for the task. From Bayesians, we have the posterior probability. Posterior probability comes from a concept introduced by Bayes, but this concept was first implemented in code by Laplace. From the principle of indifference or the principle of insufficient reason, we have prior probability, which is the probability we expect something to happen with no direct evidence, and posterior probability, which is simply the probability that something will happen based on new evidence or gained experience. From this, we have Bayes' theorem, which is a rule for updating the degree of belief when new evidence is received. What makes Bayes' theorem so special is that it allows us to calculate either the cause or effect. For instance, we can determine the odds that someone has a flu if they have a fever, and vice versa. Bayes' theorem takes the name of naive Bayes when each listed effect is independent of each other, or in other words, it is a generalization of Bayes' theorem. From analogizers, we have margin. Margin is simply the distance between a data point and a decision boundary. The goal when using margin is to find a function which splits the dataset relatively well, but also creates the largest amount of space between data points and the function. The function in this case is known as a decision boundary, where points above this boundary are marked differently than points below the boundary. This is another type of classifier. However, the larger the margin, the better the data has been split. What makes margin particularly interesting is that it resists overfitting even in very high dimensions. This is a simple landmine example to better explain the idea of margin. The dotted line alpha correctly separates all of the positive examples from all the negative examples. However, it comes dangerously close to 2 points. If these were landmines, we may not want to be as close to these points and would prefer a path which creates a wider allotted margin of error. The solid line Bravo provides that solution, and it also splits the dataset perfectly. The solution does not come anywhere near as close to any of the landmines presented in the chart, and it gives us a more clear general path.